Thermodynamics is a field of science which studies energy and how energy is converted and stored. In thermodynamics, we study how energy interacts with systems and what changes the systems undergo as a result of this interaction. So what is a thermodynamic system? A thermodynamic system is a quantity of matter. It could be solid, liquid, or gas, or a region of space which we have chosen to observe or study. So essentially, a system is whatever we want to study. Very commonly, we'll be studying single devices or a combination of devices containing a quantity of matter as our system. We always consider everything external to the system as its surroundings, and we call the surface separating the system and its surroundings the system's boundary. The boundary could be a real surface or an imaginary one. To illustrate this, let's quickly take a look at the weighted disk acting on a vessel containing a gas. If we wish to study the gas alone, our boundary would be a surface encompassing just the gas. In this case, it's an imaginary surface. And so our surrounding becomes the vessel and the weighted disk, and anything else external to the boundary. We can classify thermodynamic systems into open systems, closed systems, and isolated systems. An open system is usually a region through which mass and energy are able to pass. Open systems are used in the analysis of devices such as turbines, compressors, pumps, and so on, where mass flows through. The open system could even be something as simple as a section of a pipe through which a fluid flows. Another term for an open system is a control volume. A closed system, on the other hand, is a fixed quantity of mass which we choose to study. Since the quantity of mass is fixed, no quantity of mass can enter or leave our system, and a closed system is also called a control mass. To properly distinguish between a control volume and a control mass, let's again take a look at the weighted disk and gas-containing vessel. We're going to observe the initial state of the gas and a later state where the gas has been compressed by the disk to half its volume. If we take a region occupying half the space of the vessel in the initial space as our control volume, the effect we're going to see is that more of the gas has moved into our system, effectively doubling the amount of gas within our control volume. If we take it as a control mass, however, the focus is on the exact quantity of matter that makes up the system in the first place. So our system becomes reduced in size because the gas now occupies half of its initial volume, but it still contains the same amount of gas as we had in the initial state. So to summarize, in an open system or control volume, we are concerned with a fixed region in space and how mass and energy flow in and out of it. But in a closed system or control mass, we are concerned with a fixed amount of mass and how it behaves or moves through space. A control volume retains its volume, while a control mass retains its mass. Whenever we use the terms control volume or control mass, we call our boundary a control surface. An isolated system is a special case of a closed system where, along with mass, energy also doesn't go in or out of the system. So in an isolated system, both the quantity of mass and energy remain fixed. We already mentioned that in thermodynamics, we study the changes that systems undergo as a result of interaction with energy. But how are we able to study these changes? How do we measure these changes? We do so by observing the properties of the system. A property is a macroscopic characteristic of a system, such as mass, volume, pressure, energy, and temperature, to which a numerical value can be assigned at a given time, without knowledge of the previous behavior of the system. Simply speaking, any characteristic of a system is called a property. Properties are considered to be either intensive or extensive, and intensive properties are those properties independent of the size of the system, such as temperature, pressure, and density. Extensive properties, on the other hand, are properties which depend on the size of the system. Examples are the total mass, the total volume of the system, and momentum. For example, if I had a uniform rectangular block and I split it in half, its extensive properties such as mass and volume would also be halved because they depend on the size of the block. However, its intensive properties like temperature and density would not change. They would still retain the same value because they don't depend on the size of the block. For a system not undergoing any change, all of its properties can be measured or calculated. This gives us a set of properties that completely describe the condition of the system, and this is what we call the state of the system. At any given state, all the properties of a system have fixed values. If the value of even one property changes, we have a completely different state. In thermodynamics, we deal with equilibrium states, and an equilibrium state is one in which the system experiences no change when it is isolated from its surroundings. For a system to be in thermodynamic equilibrium, it must satisfy the conditions of mechanical, thermal, phase, and chemical equilibrium. We'll look at examples of mechanical and thermal equilibrium. If I had a vessel containing some amount of gas at a certain pressure with a piston above it, and I suddenly pulled the piston upwards, there would be a pressure difference within the vessel, and the gas would no longer be in equilibrium because the molecules would start to rearrange themselves to fill up the empty space. After some time, however, the entire space would be filled up, and the system would again be in equilibrium because the pressure would be uniform and there wouldn't be any tendency for the system's mechanical properties to change. Likewise, with thermal equilibrium, if I had a liquid control mass of uniform temperature and I dropped a hot object into this liquid, it would no longer be in thermal equilibrium because regions around the object would be hotter than the rest of the liquid. After some time, this system will attain thermal equilibrium because all of the liquid would have attained the same temperature as the object and thus have uniform temperature. Any change that a system undergoes from one equilibrium state to another is called a process, and the series of states through which a system passes during a process is called the path of the process. Let's say we had a system and we measured the temperature and pressure properties of this system. The system is said to have undergone a process since it has gone from one equilibrium state to another. But it may have passed through different successive states before it arrived at its final states. This succession of states is called the path of the process. Whenever a process occurs, the equilibrium of the system is disrupted and is then restored to a different state. We saw this in the mechanical and thermal equilibrium examples, where the equilibrium of both systems was disrupted and then restored to a different state. If, however, a process proceeds in such a manner that the system remains infinitesimally close to an equilibrium state at all times, it is called a quasi-static or quasi-equilibrium process. To illustrate this, again using the pressure and temperature states. Assuming we have a system at an initial state as indicated on the pressure-temperature diagram, let's call this state 1. And then this system undergoes a change in state, a process, and arrives at a second state. We'll call this second state state 2 and indicate it on the diagram. Between state 1 and state 2, we cannot establish any states and we cannot determine the properties of the system because during this process, the system is not in equilibrium. The pressure and temperature at different points within the system will probably vary and may be changing rapidly. So we can't exactly specify a certain temperature or pressure for the entire system at any point during the process. There really isn't any path for this process because it just jumps from one equilibrium state to the second. But what if, instead of just going from state 1 to state 2, we went from state 1 to an intermediate equilibrium state, and then to state 2? So now, from state 1, the equilibrium is disrupted, and then we jump to the intermediate equilibrium state, and equilibrium is disrupted again until we arrive at the final equilibrium state. Again, let's add 2 more states in between, so that we have more equilibrium states between state 1 and 2. Now, a path is beginning to take shape, but we're still jumping from one equilibrium state to another until we get to our final state. We still have pockets of disequilibrium between our successive states. Finally, imagine if we added as many states as possible until we almost eliminate any kind of disequilibrium. Now, what we have is a process that proceeds very gradually from one equilibrium state to another until we have our final state. It's almost as if we're making very small micro jumps from one state to another. This kind of process is called a quasi-static process or quasi-equilibrium process. A quasi-equilibrium process is an idealized process and is not a true representation of an actual process. If this is the case, then why is it so important to understand quasi-equilibrium processes? Why are we spending so much time trying to break down and analyze what a quasi-equilibrium process is? Well, it's because many actual processes closely approximate it and can be modeled as quasi-equilibrium processes with negligible error. Quasi-equilibrium processes are easy to analyze, and work-producing devices deliver the most work when they operate on a quasi-equilibrium process. In fact, most, if not all of the processes we'll be analyzing in this course will be assumed to be quasi-equilibrium processes. In thermodynamics, we often use the prefix iso to designate a process for which a particular property remains constant. An isothermal process, for example, is a process during which the temperature remains constant. An isobaric process is one in which the pressure remains constant, and an isochoric process is one in which the specific volume remains constant. When a system in a given initial state goes through a number of different changes of state or processes and finally returns to its initial state, the system is said to have undergone a cycle. Now, we're going to briefly discuss some of the most important thermodynamic properties, starting with specific volume and density. The specific volume of a substance is defined as the volume per unit mass and is given the symbol V. The density of a substance is defined as the mass per unit volume, and it is therefore the reciprocal of the specific volume. Density is designated by the symbol ρ. Next up is pressure. When dealing with liquids and gases, we usually speak of pressure. For solids, we talk about stresses. The pressure in a fluid at rest at a given point is the same in all directions, and we define pressure as the normal component of force per unit area. The actual pressure at a given position is called the absolute pressure, and it is measured relative to absolute vacuum, which is a condition of absolutely zero pressure. The atmosphere exerts pressure on any object it comes in contact with, since it is made up of gas. For this reason, most pressure measuring devices are calibrated to read zero when exposed to the atmosphere and measure pressure relative to the atmospheric pressure. This pressure is called gauge pressure, and it is the difference between absolute pressure, which is the actual pressure, and the atmospheric pressure. We have a separate video where we explain fluid pressure in detail. So if you're interested in brushing up your knowledge on pressure in fluids and you'd like to check that video out, a link to the video will be in the description. Finally, we'll talk about temperature. We're all familiar with temperature as a measure of hotness or coldness. Based on our physiological sensations, we can usually tell whether a body is hotter or colder than what we're used to. But we can't on our own express this degree of hotness or coldness numerically. More so, our senses may be misleading and we may perceive two objects to be at different temperatures when they are actually at the same temperature, or vice versa. There are materials, however, which have easily measurable properties that change with temperature in a repeatable and predictable way, and this forms the basis for accurate temperature measurement. For example, the mercury in glass thermometer. When a body is brought into contact with another body at a different temperature, heat is transferred from the body at the higher temperature to the body at the lower temperature until both bodies attain the same temperature. At this point, heat transfer stops, and the two bodies are said to have reached thermal equilibrium. The zeroth law of thermodynamics states that if two bodies are in thermal equilibrium with a third body, they are also in thermal equilibrium with each other. The zeroth law may seem very obvious and pointless to state, but it is significant because it serves as a basis for the validity of temperature measurement, where, realistically, the third body we're comparing the first two bodies to would be a thermometer. Also, the zeroth law cannot be concluded from the other laws of thermodynamics, and it precedes the first and second laws in the logical presentation of thermodynamics, which is why it is called the zeroth law. The temperature scales used in the SI and English system are the Celsius scale and the Fahrenheit scale, respectively. On the Celsius scale, the ice and steam points are assigned the values of 0 and 100 degrees Celsius, respectively, and the corresponding values on the Fahrenheit scale are 32 and 212 degrees Fahrenheit. We also have something called an absolute temperature scale, which is a temperature scale independent of any thermometric substance. This absolute scale is usually referred to as the thermodynamic scale of temperature. The absolute scale related to the Celsius scale is the Kelvin scale, and this is the relation between these scales. And the absolute scale related to the Fahrenheit scale is the Rankine scale, and this is a relation between these scales.